Okay, so in this third and final video, I want to talk a little bit about some of the associated things that come up with the general linear model, including the fact that what effect sizes mean and how they relate to parameters. I want to introduce this issue of temporal autocorrelation, what it is and what we do to deal with it, and also talk a little bit about other ways of reducing the noise that are going to be useful in improving our signal to noise ratio. So the parameters are exactly what we're estimating in the general linear model. We have the data, we have our model, we then estimate the parameters. These are the beta values, right? And once we have the beta values, we can calculate the residual parameter, the epsilon, as well. The beta values, these parameters, are effect sizes, right? So what we basically want to say is that if the beta value equals 0 or is very close to 0, that means there's essentially no relationship between the data, the bold signal that we've acquired, and the experimental paradigm, if the parameter that you're looking at is the one related to, or the one of the ones related to your experimental design. Similarly, if the beta value is 0 for a temporal derivative, it means that basically there was no extra explanatory power in including the temporal derivatives for this voxel, right? So beta values around 0 mean no relationship between this parameter and the data that we've actually acquired. Large values of beta values indicate a large effect, and it can be either positive or it can be negative. So a positive effect means that as this parameter goes up, so did the bold signal. A negative effect means, a negative value means that as this parameter goes up, the bold signal goes down. You have an inverse correlation between the two, okay? And accurately estimating these beta values is really essential for combining first level analysis, that is to say an fMRI run, together with other runs to form group analyses. So it's really important that we get these right. Often, it's also important to use the parameters to just sort of illustrate the size of the effects. And the two most common ways of doing that with fMR are what are known as peristimulus time plots. And you can see this here. This is an example from the priming study I showed weeks and weeks ago at this point, where items that were new are shown in black, items that are repeated are shown in red, and you can see that there's this reduction in the effect size during the repetition, the red items, relative to the non-repeated items shown in black. That reduction is the size of this neural repetition effect, or the priming effect. And this was, I showed you this one. This is actually from an event-related design where that effect is relatively small, but I previously showed it to you also from a block design where the effect is a little bit larger. But what we've done here is we've illustrated the effect size of the thing of interest, which in this case is this repetition priming. The other way to do this is just with bar plots, right? That is to say, you can take the parameters of your conditions of interest and then just plot them. So for instance, this was from the Dahan study where we were looking at repetition priming of words in this sort of ventral occipital temporal region that Dahan and his colleagues have referred to as the visual word form area. And you can see that, you know, when you take the parameters from the items from when they were the same word versus different word, those tend to be smaller, independent of whether it was uppercase or lowercase, than when they were two different words. And that, again, is illustrating the priming effect. Both of these are perfectly appropriate ways of showing what's happening. Peristimulus time plots are something that SPM will calculate for you. Bar plots are something that come out sort of naturally from just looking at the parameter estimates of interest to begin with. But in either case, all we're really looking at here are the parameter estimates. Those are the effect sizes. And that's really valuable because there's a difference between the statistical effect, right? So that is to say, you can have a highly significant effect with really, really small differences if the variance is super low. Or you can have a highly statistical, reliably effect if there are just big old differences between the two of them, even if there's a lot of noise. So in this case, it's kind of a middle ground. You can see that there are big differences between the same word and different words when they're in this kind of a paradigm. And the effects are sort of moderate size. They're not huge, but nonetheless, they're clear. And you can see the error bars, so you have an estimate of the amount of noise that you're looking at. So this gives you additional information beyond somebody just saying, hey, yes, there's an effect there, and it's got a p-value of 0.007. by illustrating the effect size, you can get significantly more information out of your fMRI analyses. And in fact, this is something that I'm going to return to when I talk in the latter weeks of this module, because I think that fMRI where you don't look at effect sizes is not good fMRI, and you can make all sorts of errors in that case, and it's a very important skill. But as I say, when we're looking at effect sizes, all we're doing is looking at parameter estimates. One thing I should add is that because the fMRI data, the bold signal that we get, is a relative measure rather than an absolute measure, it has arbitrary units. So one bold signal difference in this subject versus one in the other doesn't mean the same thing. It's totally meaningless. These are relative differences. And as a result, that means that these units that we're looking at are very arbitrary, right? So when you plot bold signal in terms of effect sizes, the y-axis, the units that you're looking at, are arbitrary units. It is possible to convert from those arbitrary units into something that's not arbitrary, like percent bold signal change. It actually turns out to be sort of a mildly controversial thing to be able to do, and there's lots of different solutions that are available. If you're really interested in this, I would say that Jeanette Mumford has probably done the most robust work on this that I've seen. I think it's really, really good. And she's developed methods for doing this, but none of them are built into SPM or FSL as far as I'm aware. So just be aware that when you're looking at these plots, the y-axis is arbitrary. It's meaningful, but it's not the case that anything that you see on the y-axis in one plot necessarily corresponds to what you would see in a different plot. They are arbitrary units. And with, we've talked a little bit already about residual error, this epsilon term. This is what's left over, the variance that's still in the model once you've accounted for everything that you can from your covariates of interest and your covariates of no interest. And one of the assumptions in a general linear model is that residual error is independent and identically distributed. It was known as IID in stats classes, right? But that's an assumption that's violated in fMRI data. And the reason for this is because these are time series. The data at any given time point partially relies on the data from the time point before it. That's what's known as temporal autocorrelation. It's not independent. Like 3 seconds from now, if you collect the data now and you collect it 3 seconds from now, those two things are going to be related to one another because the hemodynamic response is slow, right? If you were just measuring neural activity now and 3 seconds from now, they would be independent of one another because the neural activity time frame is on the order of milliseconds. So by 3 seconds, it's really completely independent. Not so with blood flow, right? With the bold signal, these are slower changes, and therefore there is temporal autocorrelation. The fact of the matter is that anything that you collect at time t is related to what's happened at the times before it. And as a result, we are violating this assumption of independent and identically distributed, which is going to affect our statistics. So we need to deal with this temporal autocorrelation in some sense. This is, again, another source of structured noise in our data, and we're going to refer to this as colored noise because it has a particular frequency structure. White noise would be noise that affected things equally across all frequencies. Colored noises refer to specific frequencies being more affected than others. If you've ever done work in language and speech, for instance, there's only certain frequencies that humans actually produce when speaking. So if you're trying to mask someone's speech with noise, white noise isn't a perfect thing to do because a lot of the noise is outside of the frequencies that we speak. If you just clip it at the top of our range and the bottom of our range and use those frequencies, those are known as pink noise because those are the speech frequency noise that would use to mask. So specifically, the noise pattern that we see has this what's known as a 1 over f shape. It's an inverse frequency shape, right? That is to say that the noise is dominated by low frequencies. So if you plot the frequencies from 0 up to high frequency, 0 on the left, high frequency on the right, then you get this kind of plot that you've shown here on the right where the power, the strength of the noise, is highest in the low frequencies and then drops off as the frequencies get higher and higher. That's this 1 over f shape. So if you look at that in the frequency domain, you can see it very, very clearly. You know, where I've plotted these in terms of low frequency on the left, high frequency on the right. In contrast, if you look at it in the time domain, this might be the data that you can see of on the left here from your actual, you know, pre-processed fMR data, and you can see that it looks like it's got some sort of up and down kind of block pattern here, but you can also see that it's kind of shifting up over time. That's a low frequency source of noise, the fact that it's not sort of stable. And it's not changing that rapidly. It's not going up and down quickly. It's going up and down at a slow change, low frequency. So 1 over F-shaped noise means that the low frequencies are dominating these kind of noise patterns that we see. And there are a lot of things that lead to this. One is the temporal smoothness from the HRF function. That is to say, the fact that it takes, you know, 6 seconds to peak and 20 seconds to reach its sort of baseline again, or 21 seconds. So there are slow changes that are happening due to the blood flow. There are also physiological signals that are in here. So the fact that you're breathing, that is literally your lungs are expanding and contracting as you breathe, as well as your cardiac cycles. Your heart is expanding and contracting as it pumps blood through your body. Both of those are happening at a faster rate than the TR. So they are actually faster sources of noise than we're acquiring. But because we're only sampling at a slow rate, it actually does something called aliasing. That is to say that even though it's happening at a faster rate than we're sampling it, that means that it's going to show up in our data as a low frequency signal. Historically, you used to see this examples of aliasing all the time. Whenever you would watch like a TV program and there were TV screens in the background, like in newsrooms, this would happen. You would see that there'd be this line that would be slowly running down somebody's screen in the background, which is always kind of weird because you don't see that on your screen. But this is an example of aliasing because what's happening is the TV screen is updating itself about 60 times a second, 60 hertz. But so is the one in their background. So it's being sampled too slowly to sort of get it exactly right. And as a result, it shows up as a low frequency change you can actually see in the image. This is exactly what's happening with your physiology, with your breathing and with your cardiac signal. Those are high frequency changes that are being sampled at a slow rate, the TR. And as a result, they manifest as low frequency noise in your data. In addition, there are some residual effects of head motion, and then there's also what are called point spread functions that are simply due to the way we're acquiring the bold signal in an MR scanner. So all of these things are sources of low frequency noise that lead to this kind of temporal autocorrelation. What are we going to do about it? Well, in a perfect world, what we'd like to do is just do this kind of mass univariate approach. We'd like to estimate it at each of the voxels. And then once we know what the estimate of the noise is, then we can kind of filter it out so that we're doing something optimal and sensible. But it turns out that's a hard problem to solve. So there have been various different approaches that have been done to do this. One is to say, look, it's really hard to solve that problem. So rather than estimate it, what I'm going to do is I'm going to smooth the data in time. I'm going to impose a certain temporal autocorrelation structure on it that's bigger than the existing noise that's already there. So I'm going to swamp it. And then I'm going to fix it because I know what I swamped it with, and I can filter it just to remove that. That's the pattern that SPM used in previous incarnations. So SPM did that up to, I think, about 2002. And then by 2005, the SPM5 implementation, they had implemented the second of these methods, which is a way to estimate the smoothness and apply a filter to remove it. And this is what's known as a pre-whitening approach. So rather than swamp the noise and color it with a particular noise frequency that you already know, we're going to estimate it and remove it, try to make the noise white. And then for a long time, AFNI, which is a US software package for analyzing fMRI data, just simply ignored it. They basically said, yeah, the data have temporal autocorrelation structure in it, but of the things that you can violate in terms of assumptions in your general linear model, that's not a big deal. This is kind of the ostrich head in sand approach to dealing with a problem. If I don't pay attention to it, maybe it'll go away. And obviously that's the least good of these solutions. And I don't think it's something that's in the current version of AFNI, but I'm a little bit out of date with what AFNI is doing. So when we talk about pre-coloring, the idea here is that there is some residual noise due to temporal autocorrelation in the time series, but it's really hard to estimate it accurately. And if you don't estimate it accurately, you can make it worse. So that is to say, if you don't do a good job of estimating it, and then you try to delete the noise that you think is there, some of it you'll get rid of and some of it you'll make worse, you'll amplify. So because it's a hard problem, we're just going to skip it. Rather than try to estimate it, we're going to say, look, we know roughly the sort of magnitude of this problem. I'm going to make more noise in there. I'm going to smooth the data again in time. And then because I know exactly how much I smoothed it, I can filter that data to try to remove the effect of that. And because that effect is smaller than the one that I've imposed on the data, when I remove my effect, I will also remove the noise effects that were there to begin with. This is kind of a pre-coloring strategy. And as I said, it's no longer used by any main software packages, but historically it was one that SPM adopted for half a dozen years or so. And it's important to know that this kind of approach existed, but it's also important to know nobody does it anymore. You do not smooth your fMRI data with your HRF function a second time. You do convolve your experimental paradigm with your HRF, that is to smooth it in time, to generate an appropriate model, and that's the only time you're going to use the HRF. You do not use it any additional times. If you use this kind of approach, you lose a certain amount of temporal resolution of your data. That is to say, you acquire the data every 3 seconds, but then you smooth it by something that's like 20 seconds long, then it's as if you didn't acquire it every 3 seconds because you don't have that level of specificity in your data anymore, which is why nobody actually uses it this way. The other approach that is used is you can do what's called pre-rightening. That is to say, we can acknowledge that it's a hard problem to estimate the temporal correlation in your data, but we're going to try to do it anyway. But the key thing is we want to do it in a way that's unbiased. We don't want to make matters worse. And one way to do that is to use what's called an autoregressive 1 function. And I'll explain that, obviously. So the issue is that the temporal correlation depends on the tissue type. You have different temporal autocorrelation in gray matter than in white matter, than in cerebral spinal fluid, than bone and blood, etc. And because each voxel is a combination of lots of those factors, it becomes tricky to estimate it accurately. So one approach is to say, I'm not going to do that. I'm going to estimate it in an unbiased way. I'm going to just calculate the estimate of autocorrelation over the whole brain. And I'm not going to worry about whether it's gray matter, white matter, cerebral spinal fluid. I'm just going to compute the mean autocorrelation and use that as my estimate of autocorrelation. And the nice thing about that is it's unbiased. It doesn't bias you to getting higher or lower signal in different tissue types, which is an important thing to do. And this is what's been adopted by SPM ever since 2005, the introduction of SPM5. And what they do is they use this very simple equation that will look surprisingly like the general linear model, because once again, it is a linear equation. This is what's known as an autoregressive model, and the idea here is that the activation at time t in this voxel is equal to some constant alpha times the activation that was there in the previous time point, t-1, plus noise, right? So that is to say, I'm going to assume that the only reason that I have activation in this voxel is simply due to whatever it was, the decay from what it was before. And I'm going to measure that by trying to calculate alpha. I know what activation at time t is because I've measured the data, and I know what the activation at time t-1 is because I measured the data. So if I do that over the whole time series, I can calculate what the alpha value is. And that becomes my estimate of alpha at this voxel. If I then do that over all 25,000 voxels and get 25,000 alphas and average them together, then I get an unbiased estimate of autocorrelation and in the data set. It's worth mentioning that this is what's known as an autoregressive 1 model because I've only gone one step back in time. You can do more complicated things, like you could go back n steps in time, and that's called an autoregressive n model. So an AR2 model would be if you go back one step and a second step in time. It used to be the case that SPM allowed you to do more complicated things than an AR1 model, but because the noise in the data are very low frequency, it turns out that adding steps beyond the first, like going back one, really doesn't help that much in terms of explaining the data. So now all you can estimate is an AR1 model. So again, I'm mentioning this for your information, not because you're going to use ARN models. They're not relevant to the kind of things that we're doing with FMR at this point. There's a different approach, and this is something that was solved by a guy named Mark Woolwich in Oxford, and is implemented in the FSL software package. And that is to say, you could say, yes, it's super hard to correctly estimate the temporal correlation on a voxel by voxel basis, but it's not impossible. And that's basically what he did his PhD on. He solved that problem. And what he created was a software package called Film. Honestly, I can't remember what the heck Film stands for at this point. But what it does is it provides an accurate voxel by voxel estimate of autocorrelation structure. And to do that, he had to take tissue separation very, very seriously. He had to say that, look, we're going to make a real effort to recognize how much gray matter is in this voxel, how much white matter is in this voxel, and how that changes over time. That's hopefully resolved through realignment. And by doing that, he can do his estimates, which are noisy and therefore problematic, but then he can smooth the estimates in the same tissue type. So that is to say, he could take all the gray matter voxels and take their estimates and smooth them so that locally he can get a good estimate, an unbiased estimate of autocorrelation structure in this individual voxels without taking, white matter and CSF, for instance, affecting those values. It turns out it's a hard problem. It's computationally intensive, but it's also a solved problem at this point. So if you really are keen to make sure that you're maintaining as much temporal resolution as you want, then using this kind of film approach and using the FSL software is probably the way to go. So for instance, if you're doing a really rapid event-related design, film offers you better statistical sensitivity than using an AR1 approach, because some of what's happening in your design is at a very, very high frequency, and you're losing some of that temporal resolution by using an AR1 approach. You're not losing as much as you would if you did a pre-coloring approach, but it's also not optimal. Optimal would be to use something like film. For anything other than a very, very rapid event-related design, probably the differences are reasonably negligible. Okay, and let's just talk a little bit about filtering. After you've estimated the autocorrelation structure, then what you're going to do is you're going to apply a filter which is going to try to remove that estimated autocorrelation, right? This temporal autocorrelation, leaving your data white. That is IID, right? Independent and identically distributed. One of the important things is this filter is not only applied to the data, but it's also applied to the model. So this is somewhat counterintuitive. Most people don't think of this. They think, of course, you filter the data, but if you apply the filter only to the data and not to the model, then you've made them sort of non-comparable to one another. You actually apply it to both. So this is a weird scenario. This is the only scenario where we're going to affect both the model and the data at the same time. And we're going to do this using filtering. There are going to be two types of filtering that we do. We're going to be doing autocorrelation filtering to try to remove the autocorrelation structure. But we're also going to be doing something that's known as high-pass filtering, which I'll get to in just a second. So after filtering the data and the model to remove the autocorrelation structure, you're left with white noise. That is to say, independent and identically distributed residuals. And that means that we're no longer violating this assumption of the general linear model, which is what we want. That's why we did it. So the final thing I want to talk about is just an extension of that, which is to say that we're also going to include what's called high-pass filtering in here. And that is to say that because scanner drift and physiological noise lead to these primarily low-frequency noise signals, if we use a high-pass filter, what we're going to do is we're going to filter out those low frequencies and allow the higher frequencies to pass through unaffected. High-pass filter, right? And the key with this is that the cutoff for your filter must be large enough not to affect your experimental paradigm, right? So in SPM, there's a default of 128 seconds, and we'll just sort of illustrate this. Right. So if you have a boxcar paradigm, a block design paradigm, where you have you have a normal paradigm where things are happening every 30 seconds or something like that. So there's a fairly rapid transition between doing the task, not doing the task, etc. That's what's shown on the left. If you include a standard high-pass filter, which is the red bar shown there of, in this case, 100 seconds, because that's FSL's cutoff instead of 128 seconds, which is SPM, so it would be just slightly longer. You can see that it doesn't really change the experimental paradigm very much. It goes up, it goes down, it goes up, it goes down. In contrast, let's say that you had a really long block design. So you had something that was going on for like 250 seconds. So like 4 minutes of on and then 4 minutes of off, right? So for a lot of reasons, I've already suggested that that's a very bad design. And the reason it's a bad design is because you've moved into those that period of the spectrum where you have significant amount of noise that's at those low frequencies as well, and that's going to be confounded with your experiment, right? So that was why we had to try to keep things in the blocks of 16 to 45 seconds. Longer than that, you start run into problems. Well, if you might think, well, I'll just filter it, right? I'll filter the experiment to try to remove those noise effects. But unfortunately, as soon as you do that, you're also filtering out some of your experimental design effects. And that's a real problem. And you can see that here because this cutoff, this 100-second cutoff, or 128 seconds in SPM, now is affecting your experiment. It doesn't look like it goes up and stays up. It does this kind of swoopy thing and then it goes back down. Because when you filter the data, you have to filter the design matrix. And you're filtering out some of the frequencies that are important for your experiment. In that case, what you really need to do is increase your high-pass filter cutoff to be even lower frequencies. And you can see that if you move the cutoff to being about 250 seconds, similar to your design, then all of a sudden you get the normal design back. It's sort of on, off. However, all of those noise frequencies that are still prevalent in those low frequencies are now confounded with your design. So it's a bad way to go and it's a bad design choice. But if for whatever reason you have to choose something that gives you a design like that, then you need to be aware that you have to change the default high-pass filter so that it doesn't filter away some of your experimental design frequencies as well. The downside of that is you then lose sensitivity because there's a significant amount of noise that's going to interfere with your data and therefore disrupt your sort of sensitivity in terms of signal to noise ratio. The noise is stuck intrinsic in those frequencies in your design and will be part of your experiment no matter what you do. For the vast majority of experiments and the vast majority of cases, the default cutoff of 100 seconds in FSL or 128 seconds in SPM is perfectly fine. If you've used sensible standard kind of ways of designing your experiment, that's great. It's only if you've sort of decided for one reason or another you needed to violate some of those rules of thumb that I talked about earlier in this module and produce a design that uses sort of unusual frequencies, that's when you need to think about changing your high-pass filter. Other than that, leave it alone. Okay, so in the 3 lectures today, there are a bunch of messages that I hope that you take away. One is that what we're doing with the general linear model is this kind of mass univariate approach. We're going to analyze each voxel independently, mass univariate, and we're going to use the general linear model to do it. We'll combine them again in terms of spatial maps when we talk about statistical inference. We can improve our modeling in a lot of different ways, right? So when we generate our models, first of all, we don't just assume that everything happens instantaneously as it effectively does in the neural responses. Because we're measuring a bold signal response, which is implemented via the blood, we need to convolve our model with the hemodynamic response function to take into account the lags in time that occur due to the blood flow. One of the things we need to do is avoid rank deficiency, and the easiest way to do that is to just simply don't model your low-level baseline. It's an implicit model in your design matrix. You model your task, you model your covariates of no interest, you leave your baseline alone. Otherwise, you end up with a rank deficient design matrix and you can't estimate the parameters. You don't get statistical parametric maps out. With respect to temporal autocorrelation, we're going to adopt a pre-whitening approach. Using SPM, we're going to use the AR1 model, and SPM will implement this for you automatically. It'll come up with an unbiased estimate of temporal autocorrelation structure, and it'll filter the data and the model to remove those frequencies from the data and model, leaving you with residuals which match the assumption of the general linear model, namely their IID. And then finally, the fact that we include high-pass filtering, again, on the data and the model, helps us to remove some of these noise frequencies, these low frequencies, from our statistical analysis, meaning that we improve signal-to-noise ratio. And you can see, I mean, there's a common theme here. Almost everything I've done after just the basic setup of the model was to focus on how we can better model noise sources and remove them. In some cases, we remove them through adding covariates of no interest. Temporal derivatives allow us to deal with the fact that we have differences in time for when we collect the data. Adding motion parameters allows us to deal with the fact that there are noise factors introduced through spatial realignment. And then we also use filtering approaches, including dealing with the temporal autocorrelation and including high-pass filtering to remove some of these low-frequency sources of noise. At the end, what we hope we are left with is a statistically valid model, that is to say we've taken into account all the assumptions and done them correctly, that improves our sensitivity to detect true signal, that which comes from our experiment, and remove the effects of noise so that we can detect it even better. It's definitely worth reading through Chapter 5 on statistical modeling in the Poldrack book. I would actually recommend reading it more than once. It's a complicated topic. We've covered it in some detail today. Russ and colleagues cover it in even more detail in the book. And of course, we're going to continue talking about statistics in the subsequent weeks. But that's the fundamentals today. And this is the material that I hope is very clear. And if it's not, I hope that you're very keen in asking questions about it, because if it's not clear to you, I'm sure it won't be clear to others in the class. So anything that you ask will benefit not only you, but others as well. Thank you very much for taking the time this week, and I look forward to seeing your questions on the forum.